The scenarios in this book so far have focused on linear equations, such as y equals x plus 4. In this section, you will look at how the graph changes if you replace equals with greater than or less than. 151. In the Cartesian plane shown, plot all of the ordered pairs that have an x value of 3. How many points can you find? We've looked at this in a previous scenario. One point would be 3, 0. Another point would be 3, 1, 3, 2, 3, -1, 3, -2. All the points along this vertical line have an x value of 3. And the equation that represents that line is x equals 3. We can find infinitely many points. 152. In the same plane to the right, graph all of the ordered pairs that have an x value that is less than 3. So one of those points would be an x value of 2, 2, 0, 1, 0. Any point with an x value of 2 is less than 3, so any point here or here, any point with an x value of 1, any point with 0, -1, we can plot really any point that is to the left of this blue line. Any point in this shaded region has an x value that is less than 3. And so we see something for the first time in this book. Instead of plotting points that lie along a line, we can shade in an entire section, an entire region, to show points that make a statement, a mathematical statement, true. In this case, this red region represents all of the points that have an x value that is less than 3. Now I'll continue reading. When you combine the points that lie along the vertical line in your graph above with the points that occupy the space to the left of the vertical line, these points form the solution of the inequality x is, and this symbol is less than or equal to 3. A common way to show this solution on a graph is to draw the vertical line for x equals 3 and darken the region to the left of the line. The darkened region contains all of the ordered pairs with x values less than or equal to 3. Less than 3 is the red part, equal to 3 is the blue part. 153. In the Cartesian plane, plot all of the ordered pairs that have a y value of -2. 0, -2, 1, -2, 2, -2, -1, -2, -2, -2, and any point on this blue line that is horizontal. 154. In the same plane shown to the right, graph all of the ordered pairs that have a y value that is greater than -2. Any point with a y value of -1 has a y value that's greater than -2, and that would be all the points on this horizontal line. Points with a y value of 0 are greater than -2, +1, +2. All of these points have y values that are greater than -2. So everything above the blue line has a y value that is greater than -2. 155. When you combine the points on the horizontal line in the previous graph and the points that occupy the space above the horizontal line, these points form the solution of the inequality y is greater than or equal to -2. The red part is greater than, the blue part is equal to. So this symbol combines greater than and equal to into one symbol. How can you change the graph in the previous scenario to display the solution region for the inequality y is greater than -2? So now we're taking away the equal to part, and we just want to be greater than -2. The red part is what's greater than, the blue part is what is equal to. So we want to somehow remove the part that is equal to. So let's remove the blue line. Except before we do that, if it's not there, it might be hard to figure out the boundary of the region we're shading in. So to show where the boundary is, it is common to put a dashed line to show that you're not including that line, but that line is the boundary that separates a shaded region from a non-shaded region. 156. Graph each inequality. Part A, x is greater than -4. Let's find the points for which x is equal to -4, but we don't want to include that because there is no line underneath this inequality symbol. So we will imagine where that line is by going to an x value of -4 and then going up from there with a dashed line and down from there with a dashed line. I can put arrows to show it continues in both directions. And now we can shade the points for which x is greater than -4. Points that are greater than negative 4 would be negative 3, negative 2, negative 1. X values of any point that are to the right of this blue line will be greater than negative 4. You could spend a lot of time shading, but I don't think it's important to shade very carefully. You can just draw lines going in the direction of the shaded region and that make it clear that you have shaded to the right and not to the left. Part B, y is less than 1. Let's first find all the points where y is equal to 1. That would be a y-intercept of 1, and then all these points to the right and all these points to the left. There is not a line underneath that inequality, so I'm not including the line y equals 1. I'm only including the region where y is less than 1. And that would be any point that is below this line, points that have y values of 0, negative 1, negative 2, etc. So all the points down here would be points that make that inequality true. They have a y value that is less than 1. 157. Graph each inequality. Part A. X is less than or equal to 5. Well, x equals 5 right here and here and here and down, and so I can go and make a vertical line to show all the points where x equals 5. And I'm including that because there's a line underneath the less than symbol. So I'm including this blue line, and then I want to shade points where x is less than 5. X values less than 5 would be x values of 4, 3, 2, so that would be to the left of this vertical blue line. All of these points have x values that are less than 5. Part B. Negative y is less than or equal to negative 4. Well, this doesn't have y by itself, so you're actually not ready to graph it yet, unless you want to just plug in y values and see which ones are true. Since there's a negative y in this inequality, that's the same thing as if it was negative 1y is less than or equal to negative 4. To get rid of the negative 1, to change y so there's just 1y, you can divide both sides by negative 1, or multiply both sides by negative 1. On the left, you get y. On the right, you have negative 4 divided by negative 1, which is positive 4. And now what do we do with this symbol? Well, let's suppose we just bring it down as it is. Before we move on, let's check a y value and see if it works in this inequality right here, and also works in this inequality right here. I want to make sure it makes both of them true. So y is less than or equal to 4. One number that would make that true is 3. 3 is less than or equal to 4. Now let's look at this inequality. Let's see if I replace y with a 3. Well, y is 3, but there's a negative, so it's still negative. Negative, replace y with 3. Negative 3 is less than or equal to negative 4. Is that true? Negative 3 is less than or equal to negative 4. Well, no, negative 3 is greater than. So somehow, y can't be 3. Well, that's confusing. Why didn't it work to just bring down this inequality symbol? Let's try something that's greater than 4, like 5. 5 is greater than or equal to 4. Negative 5 is less than or equal to negative 4. Negative 5 is less than or equal to negative 4. Negative 5 is less than or equal to negative 4. Well, that's true. So it seems like in this inequality, we need y values that are greater than or equal to 4. But if we look at this inequality, it's saying that y values need to be less than or equal to 4. And this happens where the relationship gets flipped whenever you divide both sides by a negative number or multiply both sides by a negative number when you are solving an inequality. So whenever you multiply or divide both sides by a negative number, you need to change the direction of the inequality. So I'm going to do that now. I'll erase this and erase part of that. Change this to greater than or equal to 4. And now we have the actual solution to this inequality. Y is greater than or equal to 4. Start with y values that are equal to 4, like this and this and this. Now I can be equal to 4, so I'm going to make it a solid line to show that I'm including all those points. And then y is greater than 4 would be y values of 5, 6, 7, points that are above that line. And there's my shaded region. 158. Circle the inequalities that would have a shaded region that includes the boundary line. What does that mean? Here's a boundary line, and it's solid, so it is included. This is a boundary line. It is solid, so it is included. When the boundary line is dashed, it's not included. So whenever we have a less than or equal to an underlined inequality symbol, then we are including the boundary line. So I want to circle any of these inequalities that have an underlined inequality symbol. That would be part B and part D. The other two, part A and part C, would be dashed boundary lines. The boundary lines are not included because these do not say equal to. It is just less than or greater than. 159. In the Cartesian plane shown, plot all of the ordered pairs that satisfy the relationship below. The y value is 1 more than the x value. Let's make a t-chart to see what this means. The y value is 1 more than the x value. So if x is 1, y is 2. If x is 2, y is 1 more, 3. If x is 3, y is 1 more, 4. How about negative 2? 1 more than that would be negative 1. Let's plot these points. 1, 2, 2, 3, 3, 4, negative 2, negative 1. They all lie along this line. 160. The points that you plotted to the right should form a line that can be represented by the equation y equals x plus 1. Okay. So every x value, if you add 1 to it, that is what the y value is equal to. The y value equals 1 more than the x value. Y equals x plus 1. In the same plane shown to the right, plot all of the ordered pairs that satisfy the relationship y is greater than x plus 1. How do we picture that? Well, let's start with this point right here. That's a point where the y value is equal to x plus 1. So if we want the y value to be greater than x plus 1, then we would go above and plot this point, or this point, or this point. All of these points would be points where the y value is greater than that point. And we can go to another point. At this point, the y value is equal to the x value plus 1. So if we want the y value to be greater than, we would shade above. All of these points have y values that are greater than x plus 1. And these points, and these points. We want y to be greater than x plus 1. The points along the slanted line are where y equals x plus 1. So all the points above have y values that are greater than x plus 1. In the previous scenario, when you combine the points on the slanted line, these, in your graph, and the points that are above that line, all of this, these points form the solution region for the inequality y is greater than or equal to x plus 1. 161. Match each inequality with its graph. Part A. Y is greater than negative 1/4 x plus 2. Well, to think about this inequality, let's first think about the equation y equals negative 1/4 x plus 2. And then look for that boundary line. We need a y-intercept of positive 2 and a slope of negative 1/4. That would be this dashed line right here. The y-intercept is positive 2, and the slope is down 1, right 4. So graph number 2, must match up with this equation. And if we look at this inequality, it says y is greater than, so we would want to shade above, and you see this shaded region is above that line. So I'll take this and match it up with this. Part B, y is greater than or equal to negative 2. Well, let me find y equals negative 2 first. That would be this. That says y is greater than, so I want to shade above this line, and you see all of this is shaded, so these must go together. Part B goes with graph number 3. Part C, y is less than or equal to x minus 3. If it just has x, then it has a coefficient of 1, which means the slope is 1, up 1, right 1, and the y-intercept is negative 3. This line has a y-intercept of negative 3, and the slope is up 1, right 1, up 1, right 1. This inequality says y is less than, so we would want to look for a shaded region that is below the line. And here's the line, there's the shaded region below it. So we can match the inequality in part C with the graph number 4. Well, we can assume that part D goes with the graph number 1, but let's confirm that that's actually the case. X is less than negative 3. So let's find a dashed line representing x equals negative 3. That would be this. And then this says x is less than, which means x value is to the left of, and we've shaded to the left. So part D goes with graph number 1. 162. Graph the two equations shown below. Part A. Y equals negative 2x plus 5. 5 is the y-intercept. So I'll go up 5, 1, 2, 3, 4, 5, and put a point there. Negative 2 is the slope. Negative 2 written as a fraction is negative 2 or 1. So I can go down 2, right 1, down 2, right 1, down 2, right 1. That's plenty. Now we can draw a line through all of that to represent all of the points for which y equals negative 2x plus 5. Part B, 3x minus 4y equals 12. There are two ways to graph this. One way is to find the intercepts. Let x equal 0 and solve for y. 3 times 0 minus 4y equals 12. 3 times 0 is 0. Minus 4y equals 12. I'll divide by negative 4. Y equals negative 3. That is how you find the y-intercept, 0, negative 3. Now let's find the x-intercept by making y equal 0. 3 times x minus 4 times 0 equals 12. 4 times 0 is 0. 3x equals 12. Divide both sides by 3. X equals 4. So x equals 4 if y equals 0. 4, 0 is our x-intercept. And now you can draw a line through those points. That's one way to roughly estimate it. The other way you can do this is take the equation and isolate y. Right now it's in standard form. Convert it to slope-intercept form. Move 3x to the other side. That gives me negative 4y equals negative 3x plus 12. Divide both sides by negative 4. Y equals negative 3x over negative 4 is positive 3/4 times x. And then 12 divided by negative 4 is negative 3. Now I can plot this by finding the y-intercept of negative 3, which we already have, and then going up 3, 1, 2, 3, right 4, 1, 2, 3, 4. There's a point. I can do that again. Up 3, right 4, 1, 2, 3, 4. Or I can go down 3, 1, 2, 3, left 4, 1, 2, 3, 4. So there are two methods that you can use to graph a line when it is in standard form. 163. Isolate the variable y in each inequality below. Part A. 2x plus y is greater than 5. 2x is positive, so I will subtract 2x from both sides. Y is greater than 5 minus 2x. So I have isolated y. I could also write it in different order. Put negative 2x first, and then plus 5. That is another way to write that. Part B. 3x minus 4y is less than 12. I'll start by subtracting 3x. Now I have negative 4y is less than 12 minus 3x, or I can put the negative 3x first and then plus 12. Now I can take the negative 4 that's multiplied by y and undo it by dividing by negative 4. Divide both sides by negative 4. I have y, and on the right side, negative 3 over negative 4 is positive 3/4 x. Then plus 12 over negative 4 is negative 3, so minus 3. And then let's talk about what to do with this inequality. Do I put less than again? No. As we saw earlier, when you multiply or divide both sides by a negative number, we divided by negative 4, divide by negative 4 on both sides, the inequality relationship becomes the opposite of what it was. Right here it's less than, so now we switch that relationship and make it greater than. That may take you some time to remember that, and that's okay. We'll keep coming back to it. When you multiply or divide both sides by a negative number, you switch the direction of the inequality symbol. 164. Graph the two inequalities shown below. Part A. Y is less than x minus 3. First, let's find the boundary line by looking at y equals x minus 3. The y-intercept is negative 3, and the slope is 1, which I can write as a fraction, 1 over 1. So I can now go from the y-intercept and go up 1, right 1, up 1, right 1, up 1, right 1, and there's my boundary line. Something like that. However, I cannot graph the boundary line, actually, because this inequality says y is only less than, so not less than or equal to, so I need to take away this line and make it dashed. I can do that by erasing it and redrawing it as a dashed line, but I can also just erase parts of it. I can start in the bottom left part of it and just erase a bit, and erase, keep going. And then it turns it into a dashed line. Now what part do I shade? This inequality says y is less than. Y values are up and down, so y is less than would be below, all the points below this line. I'll draw perpendicular to that line so it makes it clear. You don't have to draw many lines. You can draw that many. That's fine. You can, if you really enjoy, fill it in more, but you're spending more time than you really need to. Once you've drawn a few lines, it becomes clear which side of the line is shaded. Part B, 2x minus 5y is less than or equal to 10. I could find the intercepts, but I'm going to go ahead and isolate y. Right now this inequality is in a standard form of sorts. Let's put it in a slope-intercept form. 2x is positive, so I will subtract 2x. Now I have negative 5y is less than or equal to 10 minus 2x, or I can put the minus 2x first as negative 2x, and then 10 is positive, so plus 10, and then divide both sides by negative y. As I've shown you now a couple times, when you divide both sides by a negative number, the inequality changes its direction. So instead of less than or equal to, it will now become greater than or equal to. Negative 2x over negative 5 is positive 2/5 x, and then plus 10 over negative 5 is 10 divided by negative 5, or negative 2. Now I can graph this by starting with the y-intercept of negative 2, plot that point first, and then use the slope. The slope is 2 over 5, so I can go up 2, right 5. 1, 2, and then 1, 2, 3, 4, 5. I'm going off the graph if I go up 2, right 5 again, so I will change direction and do the opposite movement, down 2, left 5. 1, 2, and then 1, 2, 3, 4, 5. So there's a point. Now I can draw the boundary line. Oh, do I need the boundary line or do I want it dashed? Well, let's look at this. Oh, less than or equal to. So I can be equal to and then less than. Well, actually not less than. Let's follow my work. Right here, the inequality switched, so now it's y is greater than or equal to. Y values are up and down, so if I want to shade the points where y is greater than this line, then I shade above all of this. And I can do that carefully, or I can just go and draw enough lines that make it clear which side I have shaded from that boundary line. 165. Is the ordered pair 0, 0 part of the solution region in either graph in the previous scenario? Justify your answer using both the graph and the inequality. Well, let's start by just plotting that point. 0, 0. Is that in the shaded region? No, it's not. Let's look at the inequality. Y is less than x minus 3. Let's replace x and y with 0 and 0 to see if 0, 0 makes the inequality true. So 0 is less than 0 minus 3. 0 minus 3 is negative 3. 0 is less than negative 3. That is false. So that's another way to see that the point 0, 0 would not be in the shaded region. Using the graph, I can see that it's not in the shaded region. Using the inequality, I get a false statement. Part B. Let's start by plotting the point. 0, 0. I can see it is in the shaded region. Now I will use the inequality to confirm that. I'll write the original one. 2x minus 5y is less than or equal to 10. Replace x and y both with 0. I'm plugging in the point 0, 0. 2 times 0 is 0. 5 times 0 is 0. 0 minus 0 is less than or equal to 10. 0 minus 0 is 0. Less than or equal to 10. That is true. So that point 0, 0 would be in the shaded region of the inequality.